Hello, and welcome to another presentation of virtual video shows. I'm your host, Michael Albrecht. Today we're going to discuss Einstein's theories of special and general relativity. The program will examine those theories, but also provide a look back at the history of the last several hundred years of scientific investigation and development of ideas that provided Einstein the foundation upon which he built his theories of special and general relativity. We begin our program today with a look at Einstein and a very pivotal moment in his early life when he was in Bern, Switzerland. He was acting as a patent attorney, a patent a clerk, actually. He wasn't an attorney. He was a clerk in the patent office in Bern, Switzerland, and raising a small family. And he was working on his own mathematics and physics papers on the side in the evenings and so on. And one day in the late 1800s, he was on his way home from work, and he was leaving the downtown area, and this clock was in the background. This big clock known as the Saatglog clock in Bern, Switzerland. And there it is right there. And Einstein was conducting what he was famous for, which are thought experiments in his head. And he would play around with ideas in physics and mathematics in his mind. And on this particular day, as he was riding away on a bus, he was looking back at the clock and he was thinking to himself, the light that is bringing that clock to my eyes, that light is traveling at a certain speed. It was known by then, about 186,000 miles per second, 300,000 kilometers per second. And Einstein imagined that if he was traveling at that speed, at the same speed as the light that was bringing that light from that clock to him as he was receding from it, that he would never see what the next second or minute was, because he was essentially outracing the light and that information, and that in a sense time would freeze. So this was a big revelation to Einstein at the time, the thought experiment with the clock. And what he decided was that relativity actually should have more accurately been called invariance, because the observed speed of light was constant, actually. And the physical laws of reference frames, such as being on the bus and moving away from the clock, that was a constant. But he decided in his thought experiment that other things around him in reality were not constant, but were relative. For instance, the length, the time, the speed or velocity, the mass, and so on, the volume of objects and spatial coordinates, they were relative to each other, and they were relative to the physical laws and the speed of light, and specifically and particularly relative to observers, human beings, whoever that were observing phenomenon. So Einstein thought about naming his theories the theory of invariance, that is, things don't vary. Certain things are very constant in the physical universe. The speed of light is constant, physical laws are constant, but properties within the universe do change depending on your frame of reference. Carl Sagan, the famous astronomer from Cornell University, made the famous statement that the testimony of our common sense is suspect at high velocities. And what he meant there was a quandary I have in producing this program for you, which is that I cannot demonstrate relativity to you because we're not moving at the speeds at which relativity and relativistic characteristics kick into gear. We would have to be moving at almost or at the speed of light. So a lot of what we're going to talk about today is something that we have to use our imagination for. The famous mathematician and magician Martin Gardner said that the universe plays fair. Its tricks may operate by principles of incredible subtlety, like relativity or invariance, and we may never discover all of them, but the universe keeps performing its illusions over and over, and always by the same method. And Einstein discovered some of those methods. Here he is in his study as a younger man, born March 14th, 1897, and passed away in April of 1955. The philosopher Bertrand Russell commented on relativity theory in his book, The ABCs of Relativity, in 1959. Bertrand Russell said that understanding relativity theory begins when we can abandon preconceived ideas and concepts about time and space, our previous ways of thinking about them. It's similar, he went on to say, that when people had to adapt to understanding the conception of a round Earth instead of a flat Earth, and a sun-centered rather than Earth-centered solar system. So there have been milestones and watersheds in human history when people have had to go through a major overhaul of how we conceive of the universe and how it operates. And relativity theory presents us with another one of those milestones. Einstein published two major works on relativity. In 1905, in his early 20s, he published his paper on special relativity, which involved the study of light and a supplement to which provided his most famous equation, E equals mc squared, or energy equals mass times the speed of light squared. And then 10 or 11 years later, he produced a paper on general relativity, which dealt with gravitation and explained gravity. So let's first discuss special relativity and ask ourselves, actually, what's special about special relativity? And actually, all it meant is that it involves what are known as inertial frames of reference, moving at a constant velocity. That is, things at rest, possibly moving, at rest or moving. Imagine you're in a car, you're going down the highway at a constant rate of speed, say 60 miles an hour, and another car is going at the exact same speed. You really don't notice that you're moving with relation to that car. But if that car speeds up or slows down, or if that car makes a turn, or if you make a quick turn, you're going to feel a strong force on you. So as long as everything is moving at a constant rate in a constant direction, that is the conditions of the special relativity that Einstein was addressing with that particular theory. Again, if you're in an airplane and you're traveling along, I'm sure many of you have had this experience on a very calm flight where the plane is just moving along through very calm skies, and you don't even notice that you're moving at about 500 miles an hour. But if another plane came by, you would notice that. All of a sudden, you would notice that you're moving. Or if you look down at the ground and had something to relate your motion to, then you would start seeing the relativity of the situation. Another interesting thought experiment or way to examine special relativity and light and how it behaves. Einstein had a thought experiment involving lightning and a moving train and an observer. And so that you have to imagine that a train is going by and lightning hits over here, and the observer sees this lightning coming from here and sees lightning, another flash coming from here. Meanwhile, that train has moved. Uh, so light from point A here, as it says, will arrive at point X, which is the person in the train, before that of B, because the train is moving toward A. So the person on the train will observe the lightning from A as it is happening before that of B, which is common sense. Y, however, the observer here will see that both bolts of lightning occur at the same time because they're not moving with relation to either one of these bolts. Both of them occur at the same time, and they see both of them happen as they really are. The person on the train moving faster toward the first bolt of lightning is going to see that flash first, and then it takes a little time for this other flash at the speed of light to catch up with the train and the observer there. So that's an interesting way to try to get a general sense of how an observer is going to see things differently, a stationary observer, than the observer who's in motion. So there we start treading into the area of the intertwining nature of time and space. Further, these are called frames of reference. So to orient something in time and space, you need to have you have coordinates. In this case, an object is at rest here, and you also place that object on these various coordinates, and you can see that they're at a particular place and at a particular time. That object is at rest, so you're able to identify that. However, if an object is moving in relation to another object, then you start getting a relative motion in terms of time and space with these objects with each other. And the observer has to decide which object is moving. You've all had the experience where you might have been at a red light and in a car, and there was a car next to you, and the light turned green, but you didn't notice it. And the car next to you started moving, and you looked over and thought you were going backwards. But actually, that was only the car next to you going forward. So the relativity of that situation becomes apparent when you have two objects to compare the motion to. Again, time and space are intertwined. Einstein proposed time is dependent, essentially, on how fast you're moving through space. And we're all familiar with this. We've been on trains, planes, cars, and buses. And how do we define those speeds? We talk about 50 miles per hour, 75 miles per hour. So in other words, if you're going from point A to point B, from one town to another, for instance, and you're going very slow at, say, 10 miles an hour, time is going to seem very long. It's going to take you a long time to get there. Whereas if you're going faster, the trip will be quicker. You will cover that amount of distance, space, in a shorter amount of time. So those are kind of common sense everyday examples of where time and space are inextricably interlinked with each other. An experiment was conducted in 1971 on aircraft where they took up atomic clocks, and they set those clocks, cesium clocks, which are highly reliable and, and measure time at a very small increment. And they set these clocks to the identical time in milliseconds, and then they put the equipment on the planes, and they flew in one direction around the earth, and then they flew in another direction at another time. And what they found was that when they moved to the east, they flew with these cesium clocks to the east, that the clocks actually slowed down. They were moving faster. Then when they went west, they were going against the rotation of the earth. And the faster the speed meant that the clock going in that direction actually measured a slower time. So this was confirmation of Einstein's relativity, a concept known as time dilation. We'll continue that conversation. Uh, GPS navigation now. Our smartphones, we all have GPS on the smartphones, global positioning systems, and those systems, the satellites that send us those coordinates, they have to take into account both special and general relativity equations in order to be very accurate over time. As it says over here, if these relativistic equations were not applied, the positions would be off by some 10 kilometers or 6 miles per day. And over time, that would become extremely substantial day by day, cumulatively. So this is a real world application of Einstein's theories of special and general relativity. Another interesting effect of relativistic theory is that in atomic reactors, where we speed up elements to a very high velocity near the speed of light, as we do in this case in the CERN nuclear reactor cyclotron over in Switzerland, the faster the radioactive material is propelled, the slower its decay rate. For instance, potassium to lead, the decay rate of those atoms as they give off subatomic particles and they become lighter elements, that rate at which the atoms decay, the radioactive material, it slows down. So it actually knows that as it's going faster, time is slowing down. Its processes are slowing down. It's amazing. Meanwhile, as mentioned, 10 years after special relativity, Einstein wanted to take into account acceleration and changes of motion. Remember that special relativity dealt with a special circumstance where you just had a constant rate of speed in one direction. So you almost don't feel anything. But what he needed to take into account was if you're in an object, whatever it is, a planet, a star, a galaxy, or if you're sitting in a plane or a car and you're accelerating or you're changing directions, then you feel a force. So Einstein took those into account and came up with the general theory of relativity. And here's the equation that captures most of that in 1916. This photo down here captures one of the postulates of general relativity. In the center here, we've got a star, but behind that star is another star. But space is warped around this central star. So the light from the distant star behind this star, the light is bent, and we receive that light as if there were 4 stars around the central one. This is known as Einstein's cross. and you could Google this. Those of you that are taking notes can Google Einstein's cross, and it will describe what's going on there with what's known as gravitational lensing, as space warps around objects in the universe and bends light. So that's an interesting phenomena predicted by general relativity. So Einstein's field equations for general relativity are described here. This part of the equation over here on this side of the equals sign, it tells matter and energy how to curve around space-time, these coordinates, these functions. And on this side of the equation, we have where we tell matter and energy how to move through curved space-time. So the mathematics here describes how matter and energy move through space, especially around objects where space is warped. Einstein postulated that what we know as gravity is actually the warping of space around objects. So around stars, galaxies, and planets, what we know and experience as gravity is simply space wrapping or warping around that object. So this kind of overturned Newtonian physics and concepts of gravity, even though Newtonian physics does still hold at very slow speeds, sublight speeds. So very interesting developments. The astrophysicist John Archibald Wheeler summed up general relativity by saying that space tells objects how to move and objects tell space how to warp, creating gravity. So there you go. With John Archibald Wheeler, who I met some years ago at the University of Texas in Austin, where he was a director of theoretical physics. So very interesting. Wheeler did some collaboration with Einstein, and Wheeler is famous for coining the phrase black hole. Another bit of evidence for general relativity has to do with Venus and its perihelion point, or as it goes around the sun, that there's a slight discrepancy they noticed by a matter of seconds and minutes as yes, that should be Mercury. I apologize. I'm going to change that, but that is evidence of general relativity, because as the planet Mercury, and in fact, I can do that right now, I think. Let's see here. Yes, the joys of modern technology here. Thank you for bearing with me. And we can save that. And this is one of the beauties of science. Is that we correct ourselves when we see a mistake. So we have corrected ourselves. Thank you for your patience. And so here we see a transit of Mercury. There it is right there. And so as Mercury goes around the sun, there is something in its orbital behavior that caught the attention of physicists and mathematicians. And when they worked it out, it proved to be evidence of general relativity theory, which proved Einstein's equations. So we've looked at special and general relativity. We've talked about light, the constant nature of light and the forces of physics, and how those are what Einstein called invariant. They don't change. But other characteristics, properties of the universe, such as light, mass, and so on, the direction, they are variable and relative to each other. We're going to take a look here at the background of some of the how we arrived at some of the physics involved here. We're going to stretch back to Galileo. In the early 1600s, Galileo came up with what we call relativity theory, or invariance also, that the laws of motion are the same. They were not variable. They were constant in all inertial frames of reference. Inertia is simply the idea that an object at rest will stay at rest until it's acted upon by an outside force, Newton's first law. Or conversely, an object in motion will stay in motion until it's acted upon by an outside force. So Galileo had his form of relativity and invariance theory. He summed that up in his dialogue on the two principal chief world systems. It's interesting to note that Galileo died in 1642, and in that same year, Isaac Newton was born in 1642, came onto the scene. And of course, Newtonian relativity, based on his theories of gravity with the calculus he had developed, it was relevant. Newtonian physics is still relevant and useful at sublight speed frames of reference. He developed the laws of motion, planetary motion, and so on. And he believed that the laws of motion, time, and space were absolute, and that time and space were mutually exclusive to each other. Einstein was going to show that they actually were intimately connected. Alessandro Volta, also an Italian physicist, came along and started the process where we began to investigate electricity. And this ultimately led to Einstein's theory of special relativity. Volta, who we know as volts now in electricity, he was experimenting with electricity and magnets with batteries. He had what was known as the Volta pile here, alternating plates of zinc intermeshed with wet fabric. And so when we were able to start harnessing electricity, then we were able to start studying its properties closer. Another famous name that we use today, the amp or ampere, is of course named for Andre Marie Ampere in the late 18th, early 19th century. French physicist. He defined the unit of electric current. So all these scientists and investigators are slowly building all of this evidence. Carl Friedrich Gauss, a German mathematician and physicist, also studying electricity, magnetism, and the fields, the force fields around a moving magnet, electrical current. As we move into the 19th century, Michael Faraday, the English scientist, was pivotal in using his electromagnetic device, which was simply copper wire, magnets, and a compass. And he was able to create and define how electric currents move through a magnetic field, how magnetic fields, a moving magnetic field, will induce or create an electric current. So they were operating concurrently with each other, electricity, magnetism, and he defined how these physics behaved. Moving magnetic waves, electromagnetic waves create fields, force fields. At one point, they were called spooky action at a distance, when you have a magnet that's able to pull another magnet closer to it, and but there's nothing between them. Well, what is between them? What's pulling one to the other? Uh, Einstein called it spooky action at a distance, and they were trying to define what was that force field. Here is Faraday giving a demonstration of his device before the Royal Society in London in the early 1800s. So this is all very dramatic as it's all building up from the time of Galileo and Newton and through Ampere and Volta, Faraday, Gauss, a lot of scientists and investigators, experimenters were involved with this. I'm only touching the surface, so I encourage you to go and look this up if you're interested in delving into the topic. So Faraday is credited with conceptualizing the full electromagnetic spectrum here and how it behaves. This is what we know as the spectrum. On the spectrum right in here is what we know. This band of the spectrum, what we know is the rainbow, or the optical region. This is what human eyes can see here of it. The visible range of the electromagnetic spectrum. That's all we can see, these frequencies or wavelengths. There actually are insects and animals on Earth that are able to see frequencies and wavelengths off toward the ultraviolet, toward the infrared. And the amazing thing, one of the amazing things about the universe and modern cosmology and astronomy is that all stars and galaxies give off this entire range of the electromagnetic spectrum, from very short high energy gamma rays through shorter X-rays, ultraviolet, the visible light rays and the optical range, and then off into the longer wavelengths here, the heat, infrared, microwaves, and then long radio waves. So if we could really see the universe as it is, it would be full of information, because the spectrum not only provides these pretty colors, but those colors and information embedded within them reveal properties about the object which emitted that light. Physicists call the entire spectrum light. We tend to think of light as just the optical range, but physicists refer to light as the entire electromagnetic spectrum. So the universe is just packed with information flying around. Our eyes only see a little narrow band of it. So really, when you are out on a dark night under the stars, you could imagine that actually it's packed with information flying in all directions. So a pivotal individual in this great 19th century era of investigation and experimentation with electricity and magnetism, which laid the groundwork for relativity, is James Clerk Maxwell, the Scottish scientist. And he came onto the scene. He was an incredibly curious individual. And he studied Michael Faraday's work and Carl Gauss's, Ampere's work. And he looked into their theoretical mathematical statements. And what Maxwell did was he pulled together the work of a lot of these other scientists involving the relationship of magnetism, electricity, and light. And he developed he published a work in 1865, a dynamical theory of the electromagnetic field. He demonstrated that electric and magnetic fields, as they travel through space as waves, they move at the speed of light. So this is where Einstein is going to get a lot of fodder to develop his theories of special and general relativity. So again, we see the electromagnetic waves, the crests and the troughs, the wavelength between them, which defines the energy of them. And of course, many things in our common daily life are waves come to us. Light is a wave. Waves on the ocean, the atmosphere has waves or cyclical behavior. So this is a very common dynamic in our physical universe. So what Maxwell did that really benefited the scientific world, the community, especially of physicists, he pulled together the work of Carl Gauss and Faraday, Michael Faraday, Andre Ampere, and he formulated all of these equations. He laid them out as both integral equations and differential equations. He defined the meaning of these equations. The electric field leaving a volume is proportional to the charge inside, or there are no magnetic monopoles. Here, the voltage accumulated around a closed circuit is proportional to the time rate of change, and so on. So Maxwell was a key individual in bringing all this together. And he published that in his earlier work in the 1860s, and then he wrote a treatise on electricity and magnetism in 1873. Maxwell's equations led to practical applications like the electric grid that has built modern civilization. But the equations also held fascinating theoretical implications that led to what are known as the Lorentz transformations, and in turn laid the groundwork for Einstein and special relativity. Another British physicist, Oliver Heaviside, at the late 19th century, early 20th century, he actually reduced Maxwell's equations, which were several scientists' equations, of course, and he simplified them even further here to make them more understandable and usable. And here you could see the representations of these various characters in these equations. Heaviside is famous for saying, "Don't be afraid of infinity," which is a humorous statement. He had been asked about the possibility of particles being able to move faster than light, which we still have yet to detect. So that's an interesting aside. So Thomas Edison there in the late 1900s, he took some of Maxwell's work, Michael Faraday's work, and he built on it and pursued the practical path to help start the electric grid. Edison established the very first known electric grid in Manhattan in 1882. And it went on with the help of Nikola Tesla and various investors, Westinghouse and major banks and so on, to begin building the electric grid based on all of these equations that these scientists had been developing. Meanwhile, other scientists were extremely interested in the theoretical aspect of Faraday's work, Maxwell's work, and so on. And this is rather lengthy. Don't expect you to read all this, but Henrik Lorentz, he developed the electron theory and what are known as the transformation equations, 1904. He replaced Galilean invariance theory with Lorentz theory, which basically said that length and time are affected by velocity. When you're moving, things get weird, is basically what these equations said. So Hendrik Lorentz was another pivotal character in this drama unfolding. as was Max Planck here, the German theoretical physicist. He laid the groundwork for quantum theory and also laid out theoretical ideas which helped Einstein, along with Hermann Minkowski, another physics professor. And all of these scientists are studying how energy and magnetism, electricity, and light behave. What are their properties? How do they behave? How do they interact with each other? So this was a great drama that was unfolding in the 17, 18, 1900s. And finally, Einstein pulls it all together in his theories to the point where he was able to, when he published general relativity theory, we were then able to point the Hubble Space Telescope at various stars and prove that space warps around objects. Light, that is, space warps light as it moves around these objects in space. And here's the observed star position. This is where it looks like it is, but the real star is here. But its light is being warped as it moves around space. This object in space, this star. So again, we see how gravity is created by space warping around objects in its path. Fascinating. So here we see the Hubble Space Telescope conducting research, various experiments on light and distant objects, and has provided more evidence that Einstein's theories are correct. Here we see this beautiful telescope, the Hubble telescope. It's about the size of a school bus. It orbits Earth at about 200 miles in an elliptical orbit. Look at the beautiful Earth in the background. Look at how thin the atmosphere, the main part of the atmosphere is. It's about 50 miles in diameter, in depth. Some have likened it to a membrane around an egg, the atmosphere of the Earth. And the oceans, of course, are very life-giving. We believe that life originated in the oceans. So magnificent image here, probably from the space station or the space shuttle of the Hubble Space Telescope. Here is what's known as Einstein ring gravitational lensing around a star. So here you have a central star. It's a very massive star, and it's warping the space around it. So space is kind of enveloping around this star here. And as light comes from behind that star from a distant galaxy, you can actually see the light bent around that object. That's known as gravitational lensing. So this is further photographic and physical evidence confirming general relativity theory. Again, the Hubble Space Telescope, looking deep into space, is able to see 4 images of a supernova that's occurring around a distant galaxy. Off in the distant behind that galaxy, you have a supernova, a star exploding. And as its light comes in and passes through the gravitational field, the lens around this galaxy, that light is broken into 4 different pinpoints, and that light arrives here on Earth to our telescopes, and we're able to see further confirmation of gravitationally lensed light bending around a distant object. Further research is being conducted down in Chile at the Atacama Large Millimeter Array Telescope. You have a big international consortium with US, Japanese, European, Chilean universities and research institutes. These telescopes have been built on the top of mountains in the Andes, where the air is very clear, and they have wonderful seeing deep into space, and they've done a lot of research down there. further confirming general and special relativity. Here's a wonderful photo of Albert Einstein looking through a telescope with Edwin P. Hubble here. There's Edwin Hubble, a famous American astronomer who studied primarily galaxies and did a lot of observations and confirmations of relativity theory. And this is back in the good old days when the astronomers would actually look through telescopes. Now, of course, they largely have instruments, computers, and so on, attached to the back end, the bottom of the telescope. And nowadays, of course, they're able to hook it all up to the internet, and they can actually control the telescopes from the other side of the world and zoom in on objects that they want to study and research. So anyway, this is a classic photo from the good old days of actually looking through telescopes here, Einstein and Hubble. What a pair of incredible individuals. Again, we see a photo here of the electromagnetic fields created by the CERN atomic reactor collider, the super collider in Switzerland, where they speed up elements to near the speed of light and then crash them into each other and see what the resulting elements or particles that are created, quarks and subatomic particles. We're in a sense going back to the beginning of the Big Bang with these colliders and reinvestigating how it was all put together, how it was all triggered. And so just a great thing here, the invention, the Large Hadron Collider at CERN in Switzerland. And of course, very real world evidence of Einstein's equation E equals mc squared can be found in our nuclear bombs, which basically take mass and accelerate it to the speed of light by chemical reactions, and that causes a fission or fusion reaction depending on the type of bomb, and that releases a tremendous amount of energy. Again, here, the energy here released is a function of the mass sped up to the speed of light squared. And there you get these incredible reactions. It's simply a chemical reaction, but the destructive power is immense. Of course, now we also have nuclear reactors which operate on some of the same principles. So here in Texas, we still have, after many years, a symposium on relativistic astrophysics. This year, in December, there'll be another session of that in Prague, the Czech Republic, just to show how relevant relativity still is, and how it's still being investigated and discussed and debated. And it's a fascinating area. Einstein said at one point that he said, "If I have seen farther than other scientists, it is because I've stood on the shoulders of James Clerk Maxwell," which is a very humorous and really wonderful statement, because he's paraphrasing Isaac Newton, who was famous for saying that if I have seen farther than others, it is because I have stood on the shoulders of giants, meaning the ancient Greek, Aristotle, Plato, Eratosthenes, any number of the ancient scientists who were postulating all kind of explanations to describe how the universe operates. Human beings, of course, have just been fascinated and interested in the universe that we're a part of since we began our hunting and gathering era and looked up at the stars. And now we have all these wonderful instruments that we're able to use to investigate the minute complexities of how the universe operates. Einstein went on to say that he wanted to know God's thoughts. The rest are details. And that's an interesting concept. I share with him myself. We understand many of the laws of physics. There's much left to still understand. Einstein also said the most incomprehensible thing about the universe is that it is comprehensible, that we actually can understand the universe. But still, we'd like to know who God is, how he or she created the universe, uh, and why. And there's always some deeper layers that we can get to exploring and understanding the cosmos. And perhaps God would reply with some of Maxwell's equations. And God said differential equations, integral equations, and then there was light. And there we shall leave our discussion here today of Einstein's special and general relativity. I hope I've given you some food for thought today, and perhaps some things to investigate further on Google and books and so on. So thank you for your time, and joining me today, Michael Albrecht, virtual video shows in this continuing tour of the universe. Blessings to us all, and we'll see you next time for the next program. Bye-bye.